Welcome to this plenary session and GRA 6036. Today we'll do project 13, which is a continuation of project 11 basically. So this project contains a long introduction about stuff that should be known from project 11. And since we are continuing that project, we have to repeat some stuff before we start today's assignment. Okay, so I'll go to my R script and I download the dataset, and then notice that I call the dataset BTY because that's shorter than beauty, and now we make an indicator variable called GL for good looking, which takes the value 1 if the looks of this person is above 3 and 0 otherwise. Now we use this variable to split the dataset in two. We are not immediately going to use the two different datasets, but we can split it. So this is a dataset that only contains the good-looking people, and here is a dataset that only contains the not-so-good-looking people. So notice how we use this variable here, set it equal to 1. So this will be a true-false vector. So will this be? So this takes the value true if the person looks assessed to be smaller than or equal to 3. Remember the comma here because this is a data frame, so it has 2 dimensions, rows and columns. So we can have a look at both these data sets. So we see that in the first one, GL is equal to 1 for all the individuals in this data set and equal to 0 here. Now, then we fit these two models on the entire data set, on the whole data set. So this is BTY. So we fit these two models, so let's go to the project to see what models we are fitting. So we are fitting this model, that's what I call fit 2. Okay, and then we are also fitting this model, that's what I call fit 1. Then we are to use an F-test to test this hypothesis. So beta 4 equals 0 and beta 5 equal to 0. Which means here, if you set beta 4 and beta 5 equal to 0, these two terms disappear and you get this model. So we are basically testing whether we need a more complicated model or the null hypothesis is, well, the simple model is okay. So we do that test by ANOVA fit 1 fit 2. Now we run this. I have to fit the models first. So we run this test and we get this output. And the most, for us, the most important part of this output is the p-value right here. So we see that this p-value of 12%, 12.5% is, at most reasonable significance levels, the typical significance level is 5%. So this means that we do not reject the null hypothesis, which means that we do not reject the simpler model being true based on this test. And so now we can start the assignment. So we go to A here. So A. So the model of equation 1 estimated separately to the two data sets. Good looking and not so good looking, and the joint model of equation 2, that's this model. Both assume that the trend between log wage and experience is of the quadratic form, so this, but with potential different values A, B, and C. Explain why the F-test described above only tests whether B and C are the same for the two groups. So if we look at this output from the ANOVA function, so that's the same thing that we got here. So this output, but it might be easier to read here. We see that these two models, they are the same. Of course, the same Y, but the same, different. So that's one easy way of seeing it. So the important thing is that is that, well, I mean, they both here allow for the intercept to differ between the two groups. And they also let, I mean, the effect of experience differ. Now this model, this bigger model, lets the effect of experience differ between the two groups. Well, this model says, well, the effect of experience is the same for the two groups. So that's the difference between the two models, that this is more flexible in a sense. You can have two different effects of experience, while here we can only have one. While they do both allow for the intercept being different for the good-looking and the not so good-looking group. So we're not testing whether, well, these are, I mean, they are not different. They are not different when it comes to the intercept term. So we're not testing whether these two models are different when it comes to the intercept term. Okay, so we'll go to B, and in B we are to use an F-test to assess whether A, B, and C are the same for the two groups. And so to do that, we can estimate the two models. So we can then copy these two models, and we call these by new names, so 1, 2, and 2, 2. Okay. So we're still going to, let's be clear about what our null hypothesis is. So which not is, well, we still have the beta 4 equals 0 and beta 5 equals 0. And then we have sort of beta 0, same for the two groups. So it's so beta 0, same for the two groups, which is the same hypothesis as saying that beta 1, so the coefficient on this covariate, is equal to 0. So we can write it like this, or we could do beta 1 equal 0 and beta 4 equals 0 and beta 5 equal to 0. Because notice that, so for what we're doing when we add this this thing, remember, I mean, this is an indicator. So we're saying that, well, the not so good looking group has this intercept. So when we are allowing the intercept to differ, what I mean is that we have beta 0 is intercept for not so good looking, while beta 0 plus beta 1 is intercept for the good looking people. So now you see how they're different. So if you test, now we want to test whether this beta 1 is equal to 0, which means that, well, both groups have the same intercept. So to do that, we can remove this thing. Then we run, we fit our models, and we once more run the F-test via the ANOVA function. So this is fit 1, 2, fit 2, 2. And we get this output. So now we see, well, the p-value here is smaller than it was before, but I mean, it's still above the 5% threshold. So let's say that that's the significance level we are working with. So we do not reject, we do not reject the null hypothesis. So we still believe, well, that this model that we call fit 1, 2, which is a simple model, we do not reject the null hypothesis that this model is true. Okay, so in the next video, I'll continue this project.